Hello and welcome to today's lecture on combinatorial search. So this time I'm using Zoom instead of PowerPoint because I'm using slides by Bob Sedgwick and Kevin Wayne, who have done some really nice slides here on combinatorial search that I will present. So basically what we will be discussing is a number of different ways of systematically going through data in order to generate partial or solutions. So that can be very useful for a number of different things. So basically a lot of different problems can be solved using these techniques. So basically what we're looking at is that we will have a systematic way of what we call exhaustive search, which means that we're trying every possible element in some search space, and that we will do this using a technique called backtracking, which then allows us to generate partial solutions and then kind of continually extended these into potentially full solutions. Of course, the challenge here is that these search spaces can be very large. So in many cases, they are exponential. However, the benefit here is that we're able to prune. So if we have a partial solution, then we can check whether this partial solution, or maybe I should say instance, this partial instance can be extended to a solution. If it cannot be extended to a solution, then we can prune it, basically removing it and everything that's below it in the search tree. And by using these kind of pruning techniques, we can be able to solve a much wider variety of problems. So let's start with the problem of enumerating n-bit strings. So the problem here is that we want to process all 2 to the power n-bit strings. And in order to do this, we have to generate these binary sequences in a systematic manner. So what we will do here is that we'll have a data structure, an array called A, for representing the different bits. This array is initialized to all zeros. And then we have a very simple procedure called enumerate, which allows us to enumerate or generate all these different n-bit strings. So what we start with here is, first of all, we have kind of the base case where we have k equals n. And in that case, we are generating a full n-bit string. And now we process that n-bit string, and then we return. Otherwise, we are generating 2 different alternatives. So either we increase, so basically looking at the rest of the sequence, which means that implicitly we have a 0. Or we put the kth bit to 1, and then we generate the rest of the n-1 bit strings. And then we need to clean up, because now we have overwritten the 0 with a 1, and we had as an initial condition that it has to be 0. And if we follow this enumerate procedure, what we will do is basically generate all this string in a depth first manner. So we will generate 0, 0, 0, then 0, 0, 1, 0, 0, 1, 0, and so on and so forth. And then we can also see here how the cleanup goes after it's been done. So at the end, we're back to all zeros. Yes, and then this, of course, is the same as counting in binary from 0 to 2 to the power n-1. So here we just have a program that just prints out these strings. So that was just a warm-up example. Another interesting, so I mean, that was about enumerating all n-bit strings. What we're interested also is to do permutations. And basically, a permutation is that you have a sequence of elements, numbers, for example, and then you want to generate all possible variations of this sequence. And to provide a concrete example, for example, we can have the n-rooks problem. So in this problem, we have n rooks on a chessboard. And the problem is, how can we place these n rooks on an n by n board so that no rook can attack any other? And what this means is, of course, there's no other rook allowed in the same row or the same column as the placed rook. So here we have one example. So we have for row 0, the rook is placed in position 1. For row 1, it's placed in position 2. In row 3, it's placed on column 0, and so on and so forth. And since there are no two rooks in the same row, it means that it's enough to have a single digit to represent one row. And since there are no two columns that are allowed to be the same, it means that the same, or each number between 0 and n minus 1 should be exactly once used. So it means that every row and every column should be covered by exactly one rook. And what this leads us to is that we basically need to generate permutations of these numbers 0 to 7, or between 0 and n minus 1. All those are then legal positions of n rooks. And the challenge here is that there are n faculty number of such non-mutually attacking placements. So how do we then go about enumerating all these permutations or generating all these permutations? So we start by having the original sequence, which means 0, 1, 2, all the way up to n minus 1. And for each value of I, we swap I into position 0. So we basically take one of these n minus 2 numbers, and we swap it into the first position. And then we do the enumeration of all the remaining numbers, or all the numbers to the right of the one we just swapped in. And then we need to clean up, basically swapping back the 0 into its right position, or swapping I and 0 again. So we're back to the original. And if we do this, we will get an example such as this. So we will start with 0 and 1, then we swap in the 1 for the 0, and there is only one permutation with 0. If we have 0, 1, and 2, we can start by swapping 0 for 0, which it doesn't do anything, and then we do the permutations of all the others, and the permutations of 1, 2 is 1, 2, and 2, 1. And then we can swap the 1 for the 0, and then we do the permutation of these two, which is 0, 2, and 2, 1, 2, 0. And then we swap the 2 with the 0, and then we do the 1, 0, and 0, 1. And then we can just continue like this. And here we have the code for basically setting things up. The interesting parts, of course, is the enumerate function, which we have here. So just like in the previous case, we have the base case, basically when we have generated a full permutation, all the n positions, then we process this, and then we're done. And here we now, instead of just changing the number ones, we now have to replace all the possible numbers that we have. So we start at k, where we are currently, and we continue until we reach n minus 1. And then we exchange the current position with this alternative one. And then we enumerate all the possible sequences of length 1 shorter, or starting one position later, is maybe better to say. And then we clean up. And if we do this, we will generate sequences as this. And here is then an example of what it would look like. So for the 4 rook case, so we start with I equals 0, then it's empty. We place the first rook here, and then we place the second rook in all the possible positions. And for all the possible positions of the second rook, we place the rook on the third position, and for all positions of the third rook, we place the fourth one. And then we generate all this n faculty number of solutions. And yeah, you can look into the details, but yes, it grows exponentially, actually n to the power n, which is a rough estimation of n faculty. Here is another approach. So in this case, we're now going from n rooks to n queens. So it means that for rooks, we only need to care about the columns and rows. When it comes to queens, we also have the diagonal. And therefore, it's not sufficient to generate just all the possible permutations, but rather we have to generate all those permutations where there is no queen attacking another one on the diagonal as well. So we can use the same representation as before. So again, we represent it, so in which column, so for each row, in which column is the queen. So again, we can start by generating all the permutations, but we might reach a stage where we cannot continue. So basically, by placing the queen on that position, it will not lead to a valid solution. And what that means is that now we have found, we know that this cannot be extended to a solution. So then we do this backtracking. So basically, we go backwards, we change the position, and then we continue from the new position. So again, if we continue here, or not continue, if we repeat this search tree that we had for all the rooks. So in the rook case, all of these are solutions. But in the n queens problems, that is not the case. So for example, here we reach the board in the red circle. We see that when we place the second queen, it is in a diagonal conflict with the first one. So therefore, none of these, none of the solutions that is below it in the search tree are valid, which means that there's no point going any further, but we can just cut the search here and jump to the next, which actually also turns out to be in violation. So actually we can cut the second search tree as well, and then we go to the third, and then we can continue, and there we actually find one of the solutions. So again, we iterate through the elements, but if we reach a dead end, then we backtrack to the previous choice. Instead of going all the way down the search tree, instead we go back up and continue from there. And this is then one way of pruning the search tree, which means that we are avoiding actually looking at that part of the search tree at all. So for the n queens problem, a dead end is a diagonal conflict, and the pruning is to backtrack and thereby cutting off everything below. So here, if we look at the search tree, we can see that the search tree is now much smaller compared to before. So it means that instead of going through all these n faculty potential solutions, we only search a much smaller part of the search tree. So the way we do here is that we have to, after, so that the change to the code is in red. So what we previously had, so we have this exchange. So we have swapped the element at I and k. Now we have to check, is this a solution which can be, or sorry, is this a placement which can be extended to a solution? If there is a conflict, then there is no point in continuing, and then we just swap back and then continue. Otherwise, if it's not a conflict, then we continue. We go down that search tree. So a very small change can lead to this very efficient implementation. And here we can just see the difference in these two. So in the third row here, we have n faculty. So this is basically the number of solutions to the n rooks problem. And in the middle row, we have the number of solutions to the n queens problem. So we see that for n equals 8, there are 40,000, more than 40,000, n faculties more than 40,000, but there's actually only 92 of those that are solutions to the n queens problem. So it's much smaller. And we can also see that if we run these experiments, they are very much faster to run than just generating all the possible permutations. So now we can go back to counting. So maybe, for example, we saw in the beginning, we saw this example of counting all the n bit numbers. In this case, we're interested in generating all the n-digit base R numbers. So this is a generalization of the example we saw in the beginning. So what we need to do here is that we need to, so the beginning is the same as before. If we have generated an n-bit number, then we're done. Otherwise, we have to generate all the possible values for the kth bit or kth number. So it means that we have to generate 0 all the way up to r minus 1. And then we assign the current position to that, so the kth bit to that, and then we enumerate the rest. And now you can, of course, ask yourself, why is not the cleanup needed within the loop? And of course, the answer is that you always assign it. So you will actually start by assigning it to 0 the first time you reach the loop the next time. And then only afterwards you need to clean up. So it's pretty straightforward. Maybe a more interesting application is to generate or solve all 9x9 Sudoku problems, which means that for each row, for each column, and for each of these boxes, they should contain the numbers 1 through 9. So it means that each row should be a permutation of 1 to 9. Each column should be a permutation of 1 to 9. And each box here should also be a permutation of 1 to 9. And actually, one very nice way of solving this problem is to enumerate all 81 digits base 9 numbers. So basically what we do is that we see one board, which is 9 by 9, meaning 81 numbers, as a single 81 digit number. And R, in this case, is 9, because we're only using numbers 1 to 9. 0 to 8 or 1 to 9. And then we can do backtracking. So as soon as we have generated a partial 81-bit digit, which does not satisfy the Sudoku constraints, then we can backtrack and continue again. So for example, if we find a conflict in a row, a column, or within a box, then we have to backtrack. So for example, if we have this partial solution here, which of course is not a proper prefix of an 81-digit number, but anyway, it's for illustrative purposes. So we see this particular cell here. It cannot be a 3, it cannot be a 4, it cannot be a 5, it cannot be a 7, and it cannot be an 8. So it means if it's one, and it cannot be a 9. And if it's one of those 6 numbers, then we have to backtrack. Otherwise, we can fill in number, which means we can try with a 1, we can try with a 2, we can try with a 6. All those 3 are legal choices at this point. So if we then do this, we basically get this solution here. The only thing we need to kind of do here is to try out all the different possibilities, and we have to check if a possibility is satisfy the conditions or not. If it's a violation, then we continue. Otherwise, we continue by filling in the next cell. And then this very small and simple program is actually capable of solving Sudokus pretty fast. The next thing we will look at is subsets. So this is just like we're interested in enumerating or generating all the permutations. It's often very interesting to generate all subsets. So given n items, enumerate all the 2 to the power n subsets. And this is basically the same as counting in binary from 0 to n minus 1. And actually one way, which I've talked about earlier in this lecture, is to represent all the subsets as integers. So basically represent them as n-bit string, I mean, if you have 4 elements, it means that you need 0 to 15. So you just use the integer 0 to 15, and then you do bitwise operations to check whether each of the 4 possible bits are set or not in this integer. So then you can basically just do 4, 0 up until 15, then do something. But here we're generating the subset explicitly. So again, we will, in this case, we would basically do as we did in the beginning. I mean, basically, it is the exact same solution as generating all the binary n-bit numbers. The only difference is the way we interpret it. So the way we interpret that the ith bit is set is that the ith element is included in the subset. Otherwise, yeah, or the other way around, doesn't matter. So then we can count. So in this case, if we have 0, 0, 0, the subset is empty. If it's all ones, then every element is in there, and so on and so forth. We can also generate something called binary reflective gray code. In this case, the n-1 bit with the 0 prepended to each word, followed by the n-1 bit coded in reverse order with a 1 prepended to the words. We have both 0 and the string we want to encode, and then we have 1 and reverse the order of the string. And then we combine these two together, and then we get this gray code. And of course, again, we can generate these. And actually, they're quite useful. So they're used to count the number of turns that the wheel is making, and so on and so forth. Yeah, so again, we can do this by making a small change in the code so that we have to dynamically set the value here compared to what the previous or what the current bit is. So there are a number of alternatives. So again, the same kind of structure of the code allows us to solve a wide variety of different problems. Yet another type of problems that we can solve is to do scheduling, which is the same as doing set partitioning, which means that we have n jobs of varying length, and we have 2 machines that can carry out these jobs. And now the question is, how do we schedule the jobs to machines in order to minimize the time that the last job finishes? And this is a set partitioning problem because we take the set of n problems or n jobs and partition them in the subset which is going to be done by machine 1 and the subset which is done by machine 2, and together this covers all the different jobs. So therefore it's a partitioning. And this is actually an example of an NP-hard problem. And we can then implement this by basically trying all the different alternatives, and just like we did before. And the only thing is that when we then have filled in the machines, allocated all the jobs so that they can be completed, then we calculate the cost. So then we can calculate the cost of this, and that's it. So actually very straightforward. And it's actually quite efficient. And then, there are a large variety of different scheduling problems, and there are basically 2 ways of solving them. One is to use dynamic programming. The second one is the one we're showing here, where we basically do enumeration. So we try to enumerate all the potential solutions, and then we verify and find the cheapest one. And what we can do is to actually add more pruning opportunities. So one very common approach is to do branch and bound, which means that we keep track of the current best solution. And as soon as a partial instance is more expensive than that, there's no point in continuing. We can just cut that branch because we will never. So we know that the costs are monotonically increasing. So therefore, we can cut off that branch, and that's called the branch amount. So it's very useful. So to summarize this kind of backtracking part, so backtracking is extremely useful, can be used to solve a lot of different problems. We have seen 3 different applications. So we had n-queens. So we started out with permutations, and then we used backtracking. Then we saw the Sudoku, which is basically a counting problem, again with backtracking. So we removed those 81 digit numbers, which are not partial, cannot be solutions. And then we have scheduling, which was basically subsets, generating the subsets with backtracking. Finally, we will look at paths in graphs. We have previously talked about the Euler paths, that these are relatively easy to generate. But if we instead want to generate a Hamiltonian path, which means that we want to find a simple path that visits every vertex exactly once. So we're only allowed to visit every vertex once. Then this is a much harder problem. In fact, it's an NP-complete problem. And another example is the Knight's Tour. In this problem, we want to find a sequence of moves for a knight, so that starting from any square, it visits every square on the chessboard exactly once. And this also, again, turns into the Hamiltonian path in the Knight's graph. So instead of just moving, you have to do two steps in one direction and one in the other. So the way you can move is different, but otherwise the solution is exactly the same. So what we do here is that we provide a backtracking solution to this. So we start with a path that's Hamiltonian. So we start with a Hamiltonian path that starts in the vertex V. And then we add V to the current path. And for each of the adjacent vertices, W, we find a simple path starting at W using all the remaining vertices. And then we remove V from the current path. And this relatively simple backtracking, so basically extending depth first solution, or depth first search. So the thing here is that we need to keep track of the depth, and of course when we have the depth the same as the number of vertices, then we know we're done, and so on. And then we basically just follow the traditional depth first search approach. So this is one way of solving this problem. And what's also interesting is that, of course, that besides that, the kind of corollary, the depth first search is another way of enumerating. So it's basically a way of enumerating all the paths through a graph. We can also use the same to modify code to find the longest path rather than the shortest path or something like that. Yes. So this concludes this lecture on combinatorial search. So as I've mentioned several times, combinatorial search is an extremely useful technique that unless there is a more efficient solution, this is usually a good backup solution that you can use in very, very many problems, especially those where you have some constraints, which allows you to prune the partial solution, and thereby only having to try out a few full solutions. So please learn this technique and make good use of it. Thank you and goodbye.